And so we start here and go there and then come around. And so Josiah Willard Gibbs taught at Yale forever, more or less. He is important in mathematics and that also in chemistry, actually. A lot of his work involves what you would run into if you took a course in physical chemistry. And he received a doctorate in engineering at Cornell in 1864, which was the first doctor's degree awarded in the United States in engineering. And then he taught at Yale, as I said, from then until about 1904, so approximately, what would that be, about 40 years. And he coined the names dot product and cross product for two vectors. And today's class is talking about the dot product, and next week, Thursday's class would talk about the cross product. And he chose the names dot and cross and the symbols for them. So if you think of your two vectors u and v and write them in component form, actually you could think of them as three component vectors as I wrote them here, or they could be two component, or for the purposes of doing a dot product as we're in the process of defining it, they could be any number of components as long as they match. So you could talk about four components or whatever. The focus in this book is on vectors that are in the plane, so that's two components, or in three-dimensional space, so that's three components. But just because you don't have a geometric interpretation does not mean you can't have the concept of a vector with more components to it than that. So as I tried to present yesterday, you can either represent your vectors with the angle brackets, as the math departments like to do, or with the unit vectors I, J, and K, if it's three-dimensional, as engineers are very determined to do. And so Gibbs' dot product then is defined this way, that U dot, see that's the dot in the dot product, V, is the first component times the first one, so U1, V1, second component times the second one, third component times the third one. Notice now these are just numbers, these components. Can be 3, 4, 5, or something like that. So as products of numbers, they obey all the rules for multiplying numbers. In other words, U1 V1 is the same as V1 U1, and the same statement here. And then this in turn, with the V components first and the U components second, is what you'd mean by V dot U. So this proves that the dot product defined this way is what we call commutative in the math department, that the order doesn't matter. And it's important to note that what we will call the cross product next week does not behave this way. The order does matter on that one. But on the dot product, the order doesn't. Now, it's what a printing cash register does. For example, if you go to the store and buy 3 pounds of bananas, you'll get a receipt, 3 pounds bananas, abbreviated a little, at 59, and then 3 times 59 will be over here. 4 pounds of apples at so much, and then that'll be over here. And 2 pounds of broccoli at so much will be over here, and then you would add it up. And if you're in Ontario, Oregon, you don't pay sales tax, and that's what it would be. So what you do all the time with a itemized receipt like this is the dot product of 2 vectors. You could think of the one, which is your quantity, as an inventory vector or a supply vector. That's language you'd use in the business school courses. And so it would be 3, 4, 2 for this little example. And the price per item or unit price vector would be the prices here. And you see what you're doing, what the cash register is doing, is this times that, plus this times that, plus this one times that one, and that's Professor Gibbs' dot product. So people who are checkers in a store are doing dot products all day, every day that they work, and probably, but they have to go to college to know it's called the dot product, you see, and to have heard who first named it. But that's really all it is. And you see, the reason you could think in other situations about vectors with more than 3 components is you could think about the inventory in a big store, which would surely be thousands of different items, and there's a price associated with every one of them, a retail price, and there's also a price that the store would figure it actually has in it. So if you had a computer do the dot product, the one number would be how much the store has invested in the inventory, and the other would be what the store would say is the retail value if they could sell the whole thing out and get the asking price. So in a business context then, vectors can be many, many dimensions. And you can see that in terms of a management situation. You can think about all the stuff that Micron has that I don't begin to know anything about. And somebody somewhere upstairs should know how much each thing cost. Whether they do is another story. I'm not going there, but somebody's supposed to know, okay? So suppose that somebody does, all of that would be a vector with many, many dimensions. And then you could multiply in the dot product sense by how many items you have of each type, and you'd have a big total of money, of course. So if you're talking money, vectors don't have to be limited to 2 or 3 dimensions. If you're talking geometry as we intuitively think of geometry, then they're 1, 2, or 3 dimensions. But business-wise, they're certainly not limited. Okay, so the dot product of the 2 vectors finally here is just a single number. So that's a scalar. A number is a scalar. To have a vector, you have these arrangements of numbers, either separated this way or with the unit vectors I, j, k. And one of the reasons for the angle brackets, you see, is that this system will allow for vectors of any size, whereas this is limited. This is thinking purely of ordinary geometry, and it's limited to 3 dimensions or fewer. So for the product to be defined, the vectors have to match in length. In other words, if it's a 3-component vector and you're dotting it, the other vector has to be 3 components, and so on like that. Notice if you've taken any matrix algebra, I don't know if anybody here has, but this dot product is how you multiply matrices. If you have done that, think how you do it. And for example, you take a row of the left one and then the dot product of the first column of the right matrix, and that number is your entry in your product matrix. So I made that comment here. Now notice another thing. The dot product of a vector with itself is the squared length. See, to get the length of the vector, remember we talked about that yesterday, that's the law of Pythagoras, really. And if you're using this symbol for the length of the vector, remember the line over the letter means it's a vector, and in the book that would be a letter in boldface type. That's how you know it's a vector. So then you can use just the absolute value symbol on a vector to know that it doesn't mean the magnitude of a number, because either the line here or the fact that it's boldface type, as in the book, means it's not a number, but is a vector. So this would be the squared length, which is the dot product of A with itself, which would be A1 square, A2 square, A3 square, add them up. And this is, if it were 2 components, it's the law of Pythagoras itself. And for 3 components, you use the law of Pythagoras twice, and you get this formula for the squared length. So then the length would be the square root of this, so the square root of the dot product of the vector with itself. So now if you place remember yesterday we said that a vector is not just one arrow, it's an infinite set of arrows. There is, for every point in the plane, thinking 2-component vectors, or every point in space, if you're thinking 3-component vectors, you can put an arrow with its tail at that point that will have a given length, which would be the magnitude of the vector, and point in a certain way, which would be the direction or orientation of the vector. So the class representative for any vector U is one of the infinitely many arrows, all pointed alike and all the same length. And usually you think, for example, of the one with its tail at the origin, if you have no other particular point to determine where to place the tail. So place the class representatives of 2 vectors, U and V, tail to tail, meeting then at an angle theta. This is the Greek letter theta, where that could be between 0 and 180 degrees. See, it could be 180 degrees because that could be the representative for one family of vectors, and this could be for the other, and you put them like that, and then one's pointing, say, to my right, and one's pointing to my left, and then the angle from one to the other is 180. Other than that, you see, you typically have something more like this. So here we are with the 2 class representatives. So all the vectors that we call U are that long and slant that way, and all the vectors we call V are this long and slant this way. And then we have the angle theta between them, and apply the law of cosines to this triangle. So this is U, this is V, and this is W, which I'm thinking of as U minus V, which means it's head to head with U. If you were here yesterday, you remember that we talked about vector geometry and how to add and subtract vectors in the plane using either the triangle rule or the parallelogram rule, as we call them. So if I have the two vectors, U and V, then the third side of the triangle like this would be the vector difference. See, if you thought of forming a parallelogram, you'd have another V up here and another U like that, and then the vector sum would be this arrow. So then my squared length here would be, by the law of cosines, the squared length of this side of the triangle, the squared length of this side of the triangle, minus 2, the product of the lengths of these two sides, cosine of the angle. So you get that from the trig class, Math 144 or Math 147. And on the other hand, if you look at this vector that I've called W and dot it with itself, that's the squared length of it. So the squared length of this side is also U minus V, which is W, expressed in terms of U and V, dotted with itself, and then you work out what this would be. You see, you'd have the first dot product with the first, U dot U. You'd have the first one dot product with the second one, so that would be U dot minus V. And then you'd have the second one dotted with the first one here, minus V dot U. This is just how you do FOIL if you're multiplying in algebra two terms by two terms. And then you'd have the L of FOIL, the last product with the last. The only thing is the product is this dot product type multiplying. But other than that, it's FOIL, you see. It's first, let's see, outside would be the U and the minus V, that would be that one. The inside, minus V dot U, and then the last would be that. So that's all that is. It's FOIL with only times means in the dot product sense. So then, U dot U is magnitude square. Minus times minus is plus, and V dot V would be magnitude square. And then you have U dot minus V, which is the same as minus V dot U, because one of the things we proved here is that the dot product commutes. So you can do it U dot V or V dot U. So because of that, you can say that here. And so you have two expressions for the squared length of this side. In other words, for the same thing. You have the expression from the law of cosines up here, which is this line, and then you have what this is, which is magnitude u square, magnitude v square, and then the two of these, which are the same, so minus 2 u dot v. So if they are the same, that leaves these match, those match, that means this equals this, which I have here, and then you can divide both sides by minus 2, and it leaves you this. So the dot product is the product of the magnitudes cosine of the angle between the vectors. So since the cosine, if the angle is between 0 and 180 degrees, the cosine can be anything between minus 1 and 1, including it can be 0 if the angle is 90 degrees and the vectors are perpendicular. So the dot product can be positive, negative, or 0. If the two vectors are not the 0 vector and the dot product is 0, then that means the angle is 90 degrees and they're perpendicular. When that's the case, you say the two vectors are orthogonal. So it means they're not 0 vectors and their dot product is 0, which means in turn that the angle is 90 degrees. See, if one of the vectors could be 0 itself, then your dot product could be 0 and you couldn't say what the angle is. So we can use the dot product to compute what we call a projection of one vector in the direction of another one. And this can be either a vector projection or a scalar projection, and we'll talk about what the difference is right here, right now. But either way, what you're thinking about is you have two vectors that meet at an angle, something like this. Okay, so theta is the angle between the meter stick, say, and my pointer. And so what I'd call the projection, thinking of the pointer, in the direction of the meter stick would be the base of a right triangle. Let's see if I can, so I have an angle in here, and if I projected at a 90 degree, like I'm trying to indicate with my hand, the projection of the pointer in the direction of the meter stick would be the base here of a right triangle, which I'm asking you to imagine with my arm motion that this is the third side of. And then if you have a projection along here, there is this component, which is the thing that I'm calling the orthogonal component, orth, in my picture over here. And you can get it as a vector difference. So your projection vector is along here, and the orthogonal is this way. This is the right angle I was trying to show you with the sticks, and this would be the original vector. So the vector projection of u along v would be the vector that points along here, and the length of it would be this side of the right triangle, which would be length u cosine theta. The length itself is just a number, and that's what you call the scalar projection. This, as a vector directed along v, is correspondingly what you call the vector projection. So first of all, the vector projection, in the book, the symbolism is like this. They type PROJ. If you have your book with you, take a look there in section 12.3 where we're doing this and see how the book does print it. And you'll see the abbreviation PROJ. You'll see a letter in boldface type, like U. That's the vector you're projecting onto the other vector that would be in the subscript position, and that's the V. And in the book, that's boldface type, and that's boldface type. And that's how you know you're talking about a vector. Okay, so it's going to be this long by right triangle trig. Magnitude of the hypotenuse times cosine is the side adjacent in a right triangle. And then the direction, you remember from yesterday, if you have a vector that's not a zero vector and you divide by its magnitude, that gives you a vector that points like the original but has length 1. So it's what you call a unit vector. So this is your unit vector, V over its magnitude, that tells that this thing points like V, and this part is how long it is. So you could also, if you want to do trickery, multiply and divide by the magnitude of V. See, that's a number divided by itself. So you're just multiplying by 1, so that's legal. And so the thing to notice is if you do this, you now have magnitude U, magnitude V, cosine theta, which I rewrote over here, and then this V is your vector on top, and you have magnitude V times magnitude V on the bottom. Okay, this is V dot V, that's what V dot V is, and this times that from here is U dot V. So you can write your vector projection as a quotient of dot products times the vector that you're projecting onto, which is a handy way to say it. So really then, this is just a scale factor along this direction, saying how long the shadow is of this vector, if you thought of it that your sun was right straight overhead, and so that this would be casting a shadow. And the scalar projection is just the length of the shadow, so it's magnitude U cosine theta, and so you could go back to here and say, well, you get this vector and it's the magnitude of it. That's one way to get it. Then finally, if you thought of a vector like U here and a vector along here that has this length, which is your projection vector, then the third side here of your vector triangle is what people either call orth for orthogonal, U. It's also called U perpendicular. So you'd do it as a vector difference if you wanted to get it. It would be the u vector minus this projection vector. The book doesn't really have any problems in it, I think, that ask you to compute the orthogonal component, but you could certainly do it as the difference of this vector and this projection vector, which you get with this formula. So look at some homework. Problems 1 through 8 want the dot product, the magnitude of u, the magnitude of v, cosine theta, the scalar projection of u on v, and the vector projection of u on v. So look at problem 2. If you have the book in 12.3, problem 2. In this problem, u is 512, so you can get its magnitude. So remember what you do. Dot this with itself. So you'd have 25 plus 144, which is 169. Square root that, and that's 13. So your magnitude, again, if it's a two-component vector, you're just doing the same thing as the law of Pythagoras. Think of a triangle that's 5 and 12, and then what's the hypotenuse? So 5, 12, 13, right triangle. The other one, this is actually a unit vector. If you work this out, if you're dotting this with itself, you see you'll have 9 over 25 plus 16 over 25, and that's 25 over 25, which is 1. Or, if you prefer, you can factor the 1/5. You can write your v this way, and then you can look at the 3, 4 triangle. 3, 4, 5 make a right triangle, so then what you have is the length here, which is 5 over the 5 you factored out, and you get 1. So either way you want to look at it, the v is a unit vector. So then you do your dot product, u dot v, of the 512 vector and the 3/5, 4/5 vector. So your dot product again is the first component times the first, so that's 15 over 5, plus the second, which is 12, times the second, which is 48, 12 fours, also over 5. And so it's 63 over 5. Dot product doesn't have to be a whole number or any particular number that is something that appears commonly. So then you can get the cosine of the angle between the two vectors from what we have here, that the dot product is the product of the lengths times the cosine. So the cosine would be the dot product over the product of the lengths, which is my formula here. So my dot product is the 63 over 5. My one has length 13 and the other has length 1. So you have the 63 on top, and this 5 and this 13 make 65. And then if you wanted the angle, you'd have to use your calculator and do the arc cosine. Notice, at least when you're doing inverse cosine, if your number is positive, your angle is going to be between 0 and 90 degrees, and if your number is negative, it's going to be on past 90 degrees. So then the scalar projection, thinking u on v, is magnitude u cosine theta. See that, this part. And so we got that the magnitude of u was 13, and the cosine is 63 over 65. You don't have to find, you use the cosine here, so it isn't necessary to have figured out what the angle was and then use the calculator to get the cosine. You have the exact fraction for it here. And so you have your length of u and your exact fraction for cosine. Again, with the 65, I wrote it factored because this 13 is going to cancel that one. So it's 63 over 5. And then finally, you can do your vector projection, which is this quotient of the dot products times the v. Okay, so the dot product of u dot v again was the 63 over 5, and v in this problem is a unit vector, so the dot product with itself is 1, and well, no, and then the unit vector itself, the v, is the 3/5, 4/5. So you have this dot product over this one times this vector, and so you get a vector that looks like that. So these are kind of odd fractions, but it's just how the numbers work for the problem as given. So you can actually follow through all of these things. Okay, what I have here is a different issue. So before we go on with problem 13, do you have any questions here on my work with problem 2, I guess it was? Well, look at it for a second and I'll find these sign-up sheets somewhere. Okay, then look at what we have here. In number 13, the triangle proves to be isosceles. They don't tell us that, but we find that out. So we're talking about the triangle where we're in the plane, and there are the three corners, A, B, and C. And A is at, if this is the origin, A is at -1, 0. B is at 2 and 1 up here, and C is at 1 and -2 down here. And this, of course, is not perfectly drawn, but you should get the general idea. So what you have then, since you know the corners, is you know the three sides of the triangle and you don't know the angles. And this is, if you're looking at this in a trig class, you can solve this kind because you can use the law of cosines at least once. And get the one angle, and then after that, you can either use the law of cosines again or use the law of sines to get a second angle, and then the three have to make 180 degrees, so after you get two angles, you subtract from 180 degrees. So that's how you would all of you have done this sort of thing in either Math 144 or Math 147 or in high school maybe. So you can do this with vector methods because you can get the vectors when you know the endpoints of the vector. That's what we went over yesterday. So your vector A to B, remember that means from A to B. So that's this one with the arrow pointed like that. And so what you do is you take, to get your first component, you take this number minus that one. So 2 minus a minus 1. To get your second component, you take this number minus that one. 1 minus 0. And so you get 3, 1. Then for a then you can get the length of the vector, which would be the length of your side, again, because to get the length, you dot the vector with itself, so that would be 9 plus 1 is 10, and that's your squared length, and then you square root it. So that's how you get this. And then to go from A to C, which would be this side, you would take the first component to be C, which is 1 minus the first component here, so 1 minus a minus 1. And for your second component, you take the second coordinate here, the minus 2, minus the second coordinate there, so minus 0. So AC would be 2 comma minus 2, which points down. See, it goes 2 to the right and 2 down. So the length, again, you dot this with itself, and you get 4 plus 4 is 8, and then you take the square root. So you have length square root 8 this way, you have length square root 10 this way, and it'll turn out this one also is length square root 10. So if you went from C to B, like that, you would take this number minus that one, 2 minus 1 for your first component, this number, 1 minus this one, so 1 minus a minus 2 for your second component, and you'd have 1, 3. And so again, if you want the length, you'd have 1 and 9, which is 10, and square root that. So then you have the two equal sides, so that means these two are equal angles. From geometry, if you have an isosceles triangle, and then the angles that are at the base of the two equal sides are equal. So because of that fact, if we use the dot product to get this angle, then 180 minus that will be the total of two equal angles, so half will be each one. So we only have to get one angle here by the dot product. So then, to get this angle, if you take the dot product of the two vectors that intersect at this angle, it'll be the product of the magnitudes cosine of the angle. So the AB then again was 3,1, and the B to C was -1, well, and then the CB would be 1,3. So you can either, in using the dot product to get the lengths, to get the angle between the vectors, what I had back here when we were first doing it was the vectors tail to tail. However, it'll also work if they're head to head, because if you turn them around, all you do is change the sign to a minus on each one. So what I did to make them tail to tail, A to B was 3,1, so B to A would be -3, -1. So this is actually B to A right here. And then in the same way, B to C is the one that I have here. So now they're tail to tail. And if you work this out, you see you have 3 plus 3 is 6. And the length of each one is √10. So the product there is 10, so 3/5. So the angle B then is arc cosine of 3/5, which is this many degrees about. And then A and C are, you take 180 minus that, and then because A and C are equal angles, divide by 2, and each one is this size. So you can solve this triangle problem using the fact that you can get the cosine of the angle between two vectors if they're tail to tail or if they're tip to tip, head to head, from dot product over the product of the magnitudes. So I've used that idea here to get this angle, and then some geometry to get the other two. So where'd the sign-up sheet here go? So now we can go over here. Look at problem 31 if you have your book with you. So we're to consider a line L given by AX plus BY equals C, where C could actually be any number, and we have to assume that B is not 0 to use our vector methods. So if B is not 0, first you could say BY is, by solving, minus AX plus C. So then the Y is, if you divide by B, which we can do, would look like this. Well, you know that if you have a line in the form Y equals something times X plus something else, the coefficient here is the slope, and the coefficient over here is the y-axis intercept. That's what you call the slope-intercept form. Okay. So if you have a line given in this form, ax plus by equals c, then the slope is minus A over B. So then consider the vector AB, where the A and the B are the same A and the same B that you've used in the equation of the line. Okay, so you can either write it with the angle brackets or with the I and the J. All of these problems in this group from 31 on are talking about lines and vectors in the plane. So this is some analytic geometry for lines in the plane that is based on vector methods. So what we know now is the slope of this vector is B over A. Because if you draw the vector AB, the class representative is the arrow with tail at the origin and tip at the point that these are the coordinates of. So say here is AB, then here is your vector. And you can see for a vector pointed like this, that its slope is rise over run, so that's the B, it would be the rise, and the run would be the A. So the slope is M equals B over A. See, the arrow is referring to this vector here. And what we're after is a line then where this would be its direction vector, meaning the vector points the direction in which the line graph would run. The original line that you started with, AX plus BY equals C, would look like this for A and B laid out this way. Notice that what's happening, if you look at this, is that the one is perpendicular to the other, which is what the result is for the problem. So think of a line L then, where the slope is minus A over B, and that would come from a line with this formula for which we figured out what the slope was. So we have line L with slope capital M minus A over B. We have line script letter L over here with slope of its direction vector, which is B over A. So then you take the product of the slope of this line with this formula and the slope of the line here that has this vector AB as its direction vector. So the product of those slopes, you see, is minus 1, and that proves that this line is perpendicular to that one, which it even looks like, I think, in my picture. So that's problem 31 then, that what we've proved is this result, that if you have a vector that's given, AB, the line that's perpendicular to it uses the same numbers as the coefficients of the x and the y. And then the c can be any value. How you get to c is, it depends on what point the line goes through. So a line that's perpendicular to the vector will have this form, and then how you tell one line from another that has the A and the B on the X and the Y is from what point is on the line. We'll see that when we do a problem here in just a minute. So this is a handy result in geometry, how if you know a vector, you know the components then you can use those as your coefficients of x and y for a line that is perpendicular to this vector. A similar thing is to start with the same given vector again, AB, and get a line that's parallel to it. So the line that's parallel to the vector AB proves to be this one, bx minus ay. So you notice that what you've done is you've interchanged the order of the letters and changed one sign. That's because if you look at two vectors, AB, and the vector you get if you interchange the order of the components and make a sign change, if you do your dot product, you see what you have is A minus B and AB, and that's 0. So the dot product is 0, so these are perpendicular. It's also true if you do it this way, if you start with so you can interchange the order of the components and make one sign change. You can either, when you interchange, you can change the sign on the letter you put on the left, and that works, or you can change the sign on the letter you put on the right, because if you work this out, see what you get. So AB is perpendicular to this one, and so either statement or both together imply that you can always get a normal for a two-component vector in this coordinate, this component switching way. So that's really what we're doing, going from problem 31 to 32. So if you consider the line like this, where if you'll notice the coefficients here are these components switched, and the sign changes on the one you've put down second. So this thing is actually doing this. That's what they're really doing to get that. So, but just consider this line, solve this for y. So minus ay then is minus bx plus c. Then solve for y, and you see the slope of the line is b over a. The slope, when you have solved for y, is the coefficient of x. So this line has slope b over a, as I said here, and C can have any value. The choice of C is how you get from one line to another of parallel lines. So then look at your vector, AB, which this drawing is the same as this one again. The vector with tip at AB, the rise is B and the run is A, so the slope is B over A. So this slope and this are the same. So the slope of L that you started with, and the slope of capital L that has this as the direction vector would be the same, so they're parallel lines. So line parallel to vector AB is like this, where you use the B and the A, and then this can be any value depending on what point it goes through. So now look at 33 that goes with 31. So the direction vector is 1, 2, and using the result here, the line that's perpendicular to a given vector is going to use the components in the same order. First one with X, second one with Y, and so that's going to be 1 times X plus 2 times Y equals some value. So how do you tell what value? Well, that comes from what point it goes through. So the problem tells you that this point's to be on your line. So now what you do is you put this in for the X and this in for the Y, which I've done here. See, the X is 2, and then I have this 2, and then the Y is the 1. And that gets you the C, which is 4. So then, out of all the lines that have the same slope and are perpendicular to this vector, they all start out X plus 2Y, and you get from one to another by your choice here of C. So the one that goes through 2, 1 has C equal 4. So this is the line. If you look at the result here in 32 for the line that's parallel to the vector, 37 is an example. So the vector for all of these lines, which you'd say is their direction vector, is 1 minus 1. Because that's what the problem gives. So the line LN, back to here, has the form our result here, the line that's parallel to a given vector has AB, has the form BX minus AY. So BX would be the minus 1 times the X minus the A, which is the 1 times the Y. And then this could be any constant. These lines all slope the same way. And again, to pick this out, you have to know the point on the line. So the point this time is minus 2, 1. We use that to get the C. So we put the minus 2 in for the X and the 1 in for the Y. And so we get 2 minus 1, which is 1. So our line is minus X minus Y minus X minus Y equals the C from here. And then if you want to do algebra, you can say it's the same as this. So here's a picture. Here's your line over here. X plus Y equals minus 1. And here's your original vector, 1 minus 1. And you see the vector and the line are parallel. So you can use vector methods either to start with a vector and get the line perpendicular, or to start with a vector and get the line parallel. So when they're parallel, you'd call the vector the direction vector for your line. And that's an important concept we'll use next week and the week after. And you can also get a line that's perpendicular to a vector. Okay, so then the last thing is what goes with 45 through 47. Again, now we're still talking about lines in a plane. And what we're saying is we're thinking of two lines, L1 and L2. And for L1, there'd be a perpendicular, that you call its normal, and for L2 there would be. So the V1 would be the direction vector for line 1 and the V2 for line 2. So again, from the result of problem 31, if you have a vector, the line that's perpendicular to it uses the components of your vector as their coefficients for x and y. So if the normal for a line in the plane is AB, then the line itself is going to look like AX plus BY equals C. So if you have intersecting lines, L1 and L2, you can get the normals for each one using this idea, and then the angle between the lines is the same as the angle between their normals, because all that you've done with the angle between the lines is add 90 degrees, and then you have the normal. You've added 90 to each one, so the total is the same. So, for example, if you look at problem 45, you have line L1, 3x plus y equals 5, given. So from this idea, whatever would be the coefficients of x and y for your line, they are also the components for the vector that's normal. So if this is your line, then the 3 and the 1 are also the components for its normal. And if this is the vector L2, then the 2 and minus 1 are components for its normal. So the angle between the normals, which is what I'm getting here with the dot product, is the same as the angle between the lines, because for each of the lines you could subtract 90 degrees from the angle that the normal makes, say, with the x-axis, and you'd have the angle that its direction vector makes. So if you have two vectors, you get the cosine by the dot product over the product of the magnitudes. So you dot this, 2 times 3, you dot that. And that's the numerator, and then dot this with itself, and you have 9 and 1, so square root 10. Dot this with itself, you have 4 and 1, so square root 5. So if you simplify this, you get 1 over root 2, and then that's your cosine, and then your angle is 45 degrees. So you do 46 and 47 the same way. They're actually pretty easy, you see. You simply take the coefficients for each line to get your components, then you use this formula to get the angle between the normals, and that's the same as the angle between the lines. And after you work out for the cosine, go back to your inverse cosine to get your angle. Well, I think this is probably as much of your patience as I should try for today. And what we'll do next Thursday is called the cross product, and you use it to represent torque. Cross product is like you take a wrench to a fitting, and the product of the length of the handle of the wrench and the force you apply would be what you call torque. And the cross product of vectors is used to work problems involving the concepts like that. And it also has geometric interpretations, as we'll see next week. So I wish everyone a good week.